Hi friends, so today we are going to talk about the concept of model calibration, and this we will discuss in reference to a PD model calibration. PD is probability of default. As you might recollect, in one of the sessions we looked at the scores from a PD model. So what these scores try to do is differentiate between good and bad clients. So our target of interest is y, which can take the value 0 and 1, and you have independent variables which are x or kind of drivers or predictors which help us in predicting y. Now, when we typically create these models, there is kind of an intention to optimize some of the metrics, which can be called as, for example, accuracy metrics or discriminatory metrics. So one of the accuracy metrics can be the number of correct predictions, correct positive predictions divided by the total number of predictions. The others can be, for example, discrimination focused, which can be AUROC, which can be something like this, visualize like this: true positive rate and false positive rate. And AUROC is trying to measure from which model you're getting the highest uplift over a random model. Uh, and this obviously is AUROC is plotted over different thresholds, so you get this entire curve. Uh, However, the intention is, or the metric of interest is, how many of the bats you are able to capture using a particular threshold, or how many correct predictions you have made in different ways. However, one of the issues with such an approach can be the scores that you get. So, your regression equation is something like log of p by 1 minus p is x beta plus alpha. And the scores that you get from this equation, they may not translate into real probabilities, or they may be what is called as uncalibrated probabilities. The reason is because in arriving at these scores, what the model is trying to do is differentiate the goods and the bads, but it is not necessarily getting predictions or probabilities match what you would expect based on the data. Now, what I mean is, just to show it more graphically. For example, if there are kind of zeros and ones which are distributed like this. So a variable takes a value of 1 and 0 when x value is high or low, and you try to fit through this logistic model some sort of a curve like this. And what you're only interested in is deciding a threshold after which you are able to capture a lot of the bads with some x scores, and a lot of the goods with some lower x scores. However, what you're not measuring is how far off this predicted probability for the zeros was from zero, and how far off was this predicted probability from one. For example, if the uh, probability of let's say the prediction for this particular case was, let's say, 0.75. For this it was 0.9, and for this it was 0.55. For this it was 0.25. You're not looking at the distance between 0.75 and 1, which is the actual event. uh, and regardless of that, you club all of them into a bad and all of these into a good, and you measure how good the model is. So whatever prediction that you get for this particular instance, which is 0.75, it is not ensured through this model that the actual expectation of the probability of such a class being 1 is actually 0.75. So now what do we do in case we want to kind of also reflect on the model output in terms of its predicted probabilities? And why this might be important is, I have, for for example, in a hypothetical example here. So let's say you built a PD model where the PD or probability came out to be for two cases as zero point 0.1 and 0.25. Let's say the exposure was $100 and $50 here, and let's assume for simplicity the LGD or the loss given default is 100%. So in this case, the loss that you would expect from this first case is 1 by 10 times 100, which is $10, and from the second case it will be 2.5 times 5, which is 12.5. Uh, and as we just saw, this zero point 0.1 and 0.25 do not actually represent the actual default probability of the cases. It is just based on the score that is coming out from a model which has been tuned to classify zeros and ones. However, let's assume, without knowing how to do it, let's for a moment assume that these are the calibrated PDs. So here were our pure raw model outputs, and now we calibrate them through some procedure to get the actual probabilities as 0.15 and zero point 0.3. Now look at what happens to the losses. The same as kind of multiplied with the original exposure, this loss will come out to about $15, and this loss will come about to $15 as well. I.e., if you were using the model to decide which client to focus on, if you had just used the raw predictions from the model, you might have focused on client 2. So let's call this client 1, client 2. You might have focused on client 2. However, if you had calibrated the model properly, you actually realize that both the clients are equally risky in terms of their loss potential, and therefore you should rather focus your efforts on both of them rather only one. In some extreme cases, it can also reverse, that the decisions can be, even for example, if it was instead of 0.15, if it was just 0.16, you would still classify with a threshold of E.02 this as a non-default, which is 0, and you would classify this as 1 with a threshold of zero point 0.2 as default. But even if it was just 0.16, which is slightly different, you would have been estimating a loss of about $16, which means you probably need to focus on this case more, even though your final class attributed to this case is 0, which is non-default. And that's why kind of the calibration of the PD model is very, very important in actual business uses. Um, so that's the why part of it, and the question is then how do you do it. So there are different approaches of how do you actually calibrate the PD model, and one of the most probably intuitive ones is that you try to fit from the score that you got. So remember, the score is coming from this log odds model. The score that you get, you try to convert it into some sort of a PD measure, which is kind of related to an actual sample that you have, which has zeros and ones. So basically, what you do is you convert this score into a PD measure, which can be, for example, written like this: 1 upon 1 plus e raised to minus uh, 8 times s plus b. Um, and then what you try to do is you try to estimate the A's and the B's such that your error in terms of predicted PD is minimized. So that is generally the concept that is used for calibrating the model. And what this type of calibration is generally called as a flat scaling or sigmoid transformation, where you are basically converting your score into a PD function. Uh, so you will basically run some procedure to optimize the A and B, or sometimes called as alpha beta, to go from this score to a PD, which is closely matching with what you would expect from a sample. So this is one of the ways. This is called flat scaling, and also called the sigmoid function. There is something called as isotonic regression as well, in which instead of doing the sigmoid transformation of the score, what you do is over various score ranges, you try to bin similar ones together and take an average estimate of something like this, a monotonically increasing trend, and you define these to be actually linked to the real probabilities. In the end, what you would have is a kind of calibrated curve, just to assess how the calibration has an effect on the model. Uh, you can also visualize this in terms of a graph which is called as a calibration curve. So think of a graph like this, where here is on the x-axis you have the predictions from the model, and on the y-axis you have the actual uh, probabilities of default. So what you do is typically you define some score buckets. So let's say if your scores were in hypothetically ranging from 0 to 600 or 1000, then you bucket them into kind of constant sizes, and then you see within those buckets what was the average prediction that you made, and against that what was the actual probability of default in that bucket. In an ideal world scenario, you should expect that this is a straight 45-degree line, given you are expecting that your model's prediction is actually matching the actual predicted default probability in that bin. However, what you might get is if you just use the raw predictions from the model, you might see the classifier to go something like this. So in this case, for example, the model is saying that your prediction of probability was high, was lower, while the actual probability of default in that for that bin was even higher. So you were kind of undershooting the actual probability of default, and in some cases you might also see something like this. So in both cases, it's possible because the ranking is maintained. That is, your the ranking is not ordered, as you can see, right? The scores are going from left side to right side. The scores are not being changed. What is changed is the actual probability of default. So what that means is your AUROC and some of the other metrics will still be the same and may not vary. Uh, However, your actual predictions are varying, which will make a difference when we talk of such a business scenario. Um, and what you should therefore do is, after you run this calibration, you should check your calibration curve. As we said, this is called the calibration curve, and see if this calibration curve is closely tying out for a calibrated model to this 45-degree line. So the intention would be that post calibration, you are trying to get very, very close. So if you have an x value which is, let's say, 0.25, then you also have a actual prediction which is, or actual observed PDs as 0.25 within that bit. So this is how you would then end up checking your calibration, if that has been inappropriate or not. So thanks for watching this video. In case you liked it, please do subscribe. And as a request, if some of you are interested in learning how to do this actually using, for example, Python code, please paste your comments, and I would be happy to then also provide you and conduct a session where we will talk about coding this up or doing the calibration of the PD model in Python. Thanks a lot for your time.